Okay, this is strain example number 10, and this represents a new class of problems. This is still within chapter 9 of the textbook, still within the discussion of strain, but this is an indeterminate problem. So it's a new set of example problems and a new module on Blackboard. So the problem reads that for the system shown below, determine the stress in each bar and check for yielding. All bars have a cross-sectional area of 4 inches squared. Bars A and C are made of steel. Bar B is made of aluminum, and the horizontal bar at the bottom is rigid and does not bend in any way. Okay, so the first step in a problem like this is to try and impose statics, or try and use statics to work through the problem. So the first thing I'm going to do is I'm going to take a free body diagram of this weight at the bottom. And when I do that, there are a number of forces acting on it. The first one is the force that represents the weight of the body. So let's see, that's going to be red. So we have a weight W is equal to 420 kips. And then there's a weight in each one of the rods as well. So if we look at these rods and we assume that they're each in tension, then we have a force here that acts upwards. We'll call it P sub A. We have a force here that acts upward. We'll call it P sub B. And a force here that acts upward. We'll call it P sub C. All right. And then from the dimensions here, you can see that we have a dimension here that is 2 feet and a dimension here that is also 2 feet. So what we can do is write some equations of statics for that. The first thing I'll do is probably the simplest. I'll say that the sum of the forces in the x is equal to 0. So in that case, we end up with 0 equals 0. There aren't any forces acting in the x direction. Then the second thing that I'll do is take sum of the moments about some point. So if we call this point A here, call this point B here, call this point C there, then I'll take a sum of the moments about point B. And what I end up with there is that, let's see, we'll take that as positive, counterclockwise as positive. And we end up with, let's see, P sub C acting at a distance of 2 feet minus P sub A acting at a distance of 2 feet is equal to 0. So therefore, we end up with P sub A is equal to P sub C. And then finally, we can write the third equation that we have. Sum of the forces in the y direction is equal to 0. And there we end up with P sub A plus P sub B plus P sub C minus W equals 0. So even if we do a substitution now, if we substitute in that P sub C is equal to P sub A, then we could write this equation and we could say that 2PA plus PB is equal to 0. So since we've used all three of the equations of equilibrium that we have, and we're not able to solve for the internal member forces in the bars, this problem is said to be statically indeterminate. So we have a situation where we can't use statics alone to determine the internal member forces. So the problem is statically indeterminate. Okay, what do we do in that case? Well, if we have a statically indeterminate problem, then we can start writing relationships for the deformations in the parts. So I'm going to go back up to the original problem here. And in green, I'm going to sketch what happens when we impose a load. So we have a load here, W, that's acting downwards. And when that load acts downwards, then each one of these rods is going to stretch, and this piece down here is going to move downwards by some amount. Whoops, let me change that to blue. So we have some deformation here from its original position to its final position, and I'll call that capital delta. All right, now I can go on and I can say that this capital delta is going to be equal to the amount of stretch that we get out of rod A. So that's going to be delta A. That's going to be there. It's going to be equal to the amount of stretch that we get out of rod B. And it's going to be equal to the amount of stretch that we get out of rod C. So this equation represents our geometric compatibility equation. All right, and we're going to use that, and I'm going to move back down to the lower part of this page, and I'm going to write that again. I'm going to say that the amount of stretch that we get in rod A is equal to the amount of stretch that we get in rod B, and that's equal to the amount of stretch that we get in rod C, and that's going to be equal to the amount of displacement that we have for that bar. Now, if we go to our equation sheet, and we look at the second page of our equation sheet and zoom in a little bit, then you can see that we have here given to us the equation for the deformation of a bar. So we know that delta over here is equal to PL over AE. And if we write it for rod A, then we could say that's equal to PA times LA divided by the area of A divided by the modulus elasticity of E. And then what we can do is we can go on and say that that's equal to PB times LB divided by A sub B times E sub B. All right, now let me go back to this view. So scroll down a little bit more. What we can do is we could observe that the length of each of these rods is the same. So the length of rod A is equal to the length of rod B, so that cancels out. And we know that all the rods have the same area. So we have an area of 4 inches squared here and here, so that cancels out as well. So this equation simplifies to P sub A divided by E sub A is equal to P sub B divided by E sub B. Now, we know that the moduli of elasticity are given to us. So rods A and C are made out of steel with E equal to 29,000, and rod B is made out of aluminum with E equal to 10,000. So I could do a substitution in here now, and I could say that this is equal to PA divided by E for A, 29,000 KSI. And that's equal to P sub B divided by E for rod B, 10,100 KSI. So then here I could solve for P sub A, and I get that P sub A is equal to, let's see, what would that be? 29,000 divided by 10,100 gives me 2.871. So that's equal to 2.871 times P sub B. All right, and then I can back substitute now. If I go back up here, I can bring this equation down. Let's see, and whoops, bring it down to here. So we substitute in here, and we get that, let's see, 2 times P sub A plus P sub B is equal to W. So then we could say that's equal to 2 times 2.871 times P sub B plus P sub B is equal to W. Or, let me see, 2.871 times 2 plus 1 gives me 6.742 times P sub B is equal to W. Or finally, we could write that P sub B is equal to W, 420 kips now, divided by 6.742. And we get P sub B equal to 62.70 kips. Oops, not 70, 62.30 kips. All right, so now what we can do is go back, and we could say that we know that P sub A is equal to 2 times, we can say that P sub A is equal to 2.871 times P sub B. And we type in here 62.30 kips. And 2.871 times that gives me 178.9 kips. All right, now for the stresses, we could say that, well, and then we go back one further step and we say P sub C is equal to P sub A, and that's also equal to 178.9 kips. So we could say that the stresses, sigma A is equal to P sub A divided by the area. So that's equal to 178.9 kips divided by 4 inches squared. So when we calculate that, we get a stress of 44.71 kips per square inch. That's also equal to sigma C. And then we can finally write that sigma B is equal to P sub B divided by the area A sub B. That's equal to 62.30 kips divided by 4 inches squared. And that's equal to, let's see, 62.3 divided by 4 gives me 15.58 KSI. So let me erase that for a second. Go over here and write it in here. So sigma C is also equal to that. So the last part of the problem asks us to check for yielding. And this is important because the relationship that we used for our deformation, this value here of delta equals PL over AE, is a function of Hooke's law. And if we go back and look at our stress strain curve that we have for material, we plot strain on the horizontal as the independent parameter, stress on the vertical as a dependent parameter, and we end up with, for steel and for aluminum, a curve that looks kind of like that. So that's more for steel than it is for aluminum, but anyways. And the slope of this line is the modulus of elasticity E, and from that we end up with Hooke's law that sigma is equal to E times epsilon, and from that we end up with delta is equal to PL over AE. So the reason why it's important to check for yielding is that this equation, sigma equals E epsilon, or delta equals PL over AE, is only valid when the stress is less than the yield stress. If we stress this beyond yielding, then that equation for Hooke's law is no longer valid. So if we go back to the original definition of the problem, it says that the steel has a yield stress of 50 KSI. So this is less than or equal to the yield stress sigma sub y. I wrote it as F sub y in the problem definition, less than 50 KSI. So that means that Hooke's law is still valid for that. And for bar B made out of aluminum, sigma sub y was equal to 30 KSI. So we can say that neither of the two materials or none of the three bars has yielded. Oops. So therefore, the solution is valid. So to summarize, the solution problem here, we start off by looking first at statics to see if we could determine the internal member forces. We can't use statics alone in this case to determine all the internal member forces, so we have to go to our second tool in our toolbox, geometric compatibility. And then finally, we have to use the third tool in our toolbox is force deformation relationship, or Hooke's law, or constitutive relationship. Three different names for the same thing, constitutive relationship. So I'll write down here in parentheses Hooke's law. So we've used each one of these in the past. We've done a lot of work with statics. We've done some problems where we've used geometric compatibility. We've done some problems where we use constitutive relationships. But the thing that sets these problems apart is that in these problems we have to use all three, and then we have to usually go in at a final step and do some back substitution. And in this case, we had to check for yielding to make sure that our relationships that we're using are still valid. Okay, that's the end of this problem.